We're joined this evening by Professor Poul Christoffersen, who's a glaciologist who specialises in ice sheets and climate change. He was a professor at the University of Cambridge before joining the University of Tasmania in 2023. At UTAS, Paul is a member of the Centre for Excellence in Antarctic Science and the Australian Antarctic Program Partnership. He's received a major EU grant from the European Research Council to investigate the effect of climate change in the Greenland Ice Sheet. And he's also a lead scientist on the international Thwaites Glacier collaboration in Antarctica, funded by research agencies in the UK and the US. Both Thwaites Glacier and some previous work in the Pine Island Glacier are within the Amundsen Sea region of West Antarctica, and his work there has contributed to a better understanding of some of the most vulnerable drainage basins in Antarctica. I'm sure Professor Christoffersen will have plenty more details for us to discuss throughout this evening. Our interviewer for this evening is Dr. Adrian McCallum, who currently serves as Head of Engineering at the University of the Sunshine Coast and manages courses in soil mechanics, geotechnical engineering, weather and climate. He's fortunate to have led a life of adventure and exploration around the globe and is an expert in remote area science and engineering. He holds a PhD from the Scott Polar Research Institute, University of Cambridge, and additional degrees in oceanography, meteorology, and civil engineering. With that, I will throw to Dr. Paul to dive into his presentation.
Thank you very much, John, for that warm welcome. Maybe Adrian, I can ask you kindly to have a look on the chat if there's any questions. I might not be able to keep an eye on that while I give the presentation. All right, let me just share my screen. Is that coming out in?
Yep, that's good, Paul.
That's good. Okay, thank you. Thank you for the welcome and giving me the opportunity to talk about things that I care about and are passionate about, things in my professional life, and also things that I think about when I'm not at work. Sometimes difficult to draw the distinction. Now, today I'm going to talk about ice sheets and predominantly the Antarctic ice sheet, because we are closer to that, and Antarctica is a place that has a rich history tied to Australia, and Australian territory in Antarctica is really an immense sector of this continent, and that's not to be forgotten, of course. So I've got a few slides on that. I don't really think I need to add a whole lot more to the introduction. I wasn't too sure whether I should talk a little bit about myself, but I've grew up in Denmark, studied in Denmark, came to Australia from a meandering path that was via New Zealand, the US, and quite a few years in the UK, where I was based in Cambridge. I'm drawn to Australia and to Tasmania for work reasons, for professional reasons, and the lifestyle that Tasmania offers. Of course, it's a beautiful, beautiful island that I can't get enough of. But let me introduce the topic. I'm going to talk about the Antarctic ice sheet and its role in global sea level change. And I've got a few slides that focuses specifically on sea level rise around Australia. If we just go and look at the observed over the last, say, 50 years, we can calculate an average value of how much sea levels globally have risen, and that's approximately 2.3 millimeters per year on average. If we look specifically at this rate in the last 20 years, that increase is nearly doubled or starting to approach 4 millimeters per year. And in this period, alpine glaciers peppered around mountain ranges in South America, Himalaya, Europe, North America, and New Zealand, and many places, those glaciers have shrunk and become smaller. They have retreated to higher elevations where it's colder. But the biggest change really has come from the great ice sheets in Greenland and Antarctica. So in the 1990s, we had ice sheet contributions from Greenland and Antarctica and mountain glaciers that was about just a little less than half of the total observed. And I'll come back in the next slide to what the other factors are. But my point with this slide is to really put emphasis on the fact that ice melting now is 2/3 of the observed rate of sea level rise, and these contributions are growing. So we've got a faster contribution of fresh water that was previously locked up as ice in continent and mountain ranges, and are now melting and running off into the global ocean. So one of the big tasks for me as a glaciologist is to try and come up with ways in which we can understand these contributions better as we observe them. But the really challenging task is to enable projections of what sea level rise might be in the future. And that's a really complex and difficult thing to do. And there's quite significant amounts of uncertainty tied to these projections, apart from saying that we know the sea level rise is happening and will continue to take place over the coming decades and centuries, but we are not at all certain about what the magnitude will be at any given point in time in the future. So ice is melting, that's the big contribution, both from glaciers, as we can see here in the background, but also from the great ice sheets. And other contributions that cause sea levels to rise is that the ocean can expand when it stores heat, and a significant amount of the additional heat that is contained in the atmosphere end up being stored in the ocean. So thermal expansion is another very significant contributor. We also have water stored in land and groundwater reservoirs that can grow and shrink according to droughts, wet periods. Land use is an important contributor to the continental side of things. And we have tectonic effects associated with continents going up and down naturally due to the way the continents are shifting. And that's a really big part of the sea level equation in a place like New Zealand, but it's less of a significant factor in Australia, which is a very stable continent. So if we look at observations around Australia, the left figure shows the observed rate of sea level rise from 1966 to 2019. And as you can see, these are actually not uniform rates. We often talk about global sea level rise, but actually the things that we as scientists are starting to think more and more about is sea level as a local factor, if not a regional factor. The fact that there's different land uses, different continental factors, but also the ice sheet contribution actually will vary from location to location. And that's because there are elastic aspects in Earth's deformation when we unload from the melting of ice that will cause a different type of response in the far field. And this is as a phenomenon we call fingerprinting. So we can fingerprint the signature sea level rise when we lose ice in Greenland or a specific part of Greenland, and it will be a different influence it will have around Australia compared to different drainage basins around Antarctica. Now, one of the key points that I wanted to just show with this figure here from Ben Haig's work, who's now at the Met Office, but did this work in Monash recently as a PhD student, is a very nice paper on recent Australian sea level rise and factors. But if we go to the right-hand side of the diagram, you can see that we have more observations in the period 1993 to 2019, but we can also see that the rates have increased. The color bar looks a little bit the same, but it is actually because the magnitude of the color scale is quite different from the two figures. I put the little red arrow in to indicate that The red color on the left-hand side is 3 to 4 millimeters per year on average of sea level rise, whereas the right-hand side is the darkest red color is 6 to 7 millimeters per year on average of sea level rise in that period. So complex, spatial, interesting, concerning trends that vary from state to state and region to region around Australia. And we are trying to elaborate on these observations to, in due course, have predictions that can be locally tied to ice losses in specific sites. Australia, of course, also has an incredibly interesting indigenous history of sea level rise that's contained in the oral stories. And I can see Patrick was in the audience, and Patrick, I did enjoy your book, which was one of the first books that I read when I came to Australia. I was really hungry to learn more about the history of Australia and the sea level history and the knowledge that's contained in the indigenous stem that goes back more than 10,000 years. Just completely blew me away. So one thing that I'm really fascinated about and would love to do in my research is to try and link the spatial information, the geographical information that Patrick has teased out of the oral traditions, of which there are 30 something now around Australia. And these observations that we know are very geographically varied, and the projections that we are producing today that are somewhat uniform, but we need to make them spatial in style and well suited for policymaking, adaptation, and mitigation aspects related to addressing sea level rise locally around Australia. So, So let me just talk a bit about Antarctica, and I thought I'd start by showing the surface, and that's probably a somewhat dull figure to the left because it's just an immense amount of fresh water that's stored down there as ice, and some of that ice sticks up over sea level rise, and that's why it poses a threat. It's stored over sea level, and that's why when it melts, it poses a threat to coastal regions in terms of sea level rise. But there's also parts of the Antarctic ice sheet that goes far below present-day sea level, particularly in the western side. And that means that some of that ice is already displacing ocean, so it will contribute less in that sense to sea level rise when it's actually lost. But the ice that sticks down so deep is more buoyant, and it poses an additional risk because we can lose that ice much more rapidly than if ice simply melt due to solar radiation and warm airflow and so forth. So there is a dynamic instability associated with ice that is grounded far below sea level. And I'll try to explain that towards the end of my talks through some graphical displays. It's an important part of my talks to try and explain why we think that there is a risk of ice sheet instability in Antarctica, because it sets Antarctica on its own path relative to Greenland, where a lot of ice is also melting, but we don't have that dynamic instability that we think it poses a risk to coastal regions in terms of sea level rise if ice sheet contribution starts to accelerate significantly faster than what we are observing them to be today. So when I talk about ice that's grounded below sea level, should I try and use my, I think I've got a little sliding thing. Laser pointer. Can you see this pointer here? Yep. So first of all, we have the West Antarctic ice sheet over here. It's the smaller of the two ice sheet, the East Antarctic ice sheet, which is grounded on a continent as opposed to on the seafloor is the larger of the two. So the West Antarctic ice sheet, you can see with this color scale here, is grounded several kilometers below sea level rise. So we call it marine-based. So it's a marine-based ice sheet, and it's marine-based ice sheets that we suspect could be more unstable than other ice masses. When we say that the East Antarctic ice sheet and the ice in the Australian territory is sort of, it was for many years seen as being a bit dormant and slow responding. But that's actually something that we are revising now, because there are large parts of East Antarctica where there are very significant drainage basins that are also grounded far below sea level. So you can see that with the blue colors in this area, particularly the Wilkes subglacial basin, with Cook and Ninnis Glacier being really interesting locations for future field work. The Aurora subglacial basin here with Totten Glacier, Denman Glacier, and some of the glaciers that are most studied. We also have sorry, I forgot the name now, but anyway. But the Amory ice shelf is what I want to highlight out on the top part of the diagram here. So if we start to compare setting, the bed topography, we can also start to look a bit about how that compares to the way the ice is moving. So in the left-hand diagram, you can see with the colors, the speed of the ice flow as observed with satellites. And we can see through this colored magenta, blue to magenta line that we've got ice flowing and draining these river-like systems from the interior of the ice sheet. So we call them sometimes ice streams. And an ice stream is a glacier that's flowing fast and surrounded by slower moving ice, as opposed to a sidewall or mountainside or so forth. So if ice flows fast through other ice, we call it ice streams. So these ice streams drain the interior of the ice sheet that keeps receiving snow, and is where the ice is forming and being produced, and then it's transported towards the coast through these glaciers and out and ice streams, ultimately to end up in what we call ice shelves. And ice shelves are the extensions of the grounded ice sheet that floats on the ocean. And there's two very large ice shelves. In this part down here is the Ross Ice Shelf, 400,000 square kilometers, about the size of France. And Filchner-Ronne Ice Shelf up here, also of substantial ice shelves. But ice shelves actually cover over half of the coastline of Australia. So these floating extensions to the ice sheet is really important. And I'll try and show some slides later on that explains how significant these floating extensions are to holding back the grounded ice that would flow faster were it not for these floating fortresses that are protecting the ice sheet. But it's also where the ice sheet meets the ocean, and it's where the ice sheet melts the most. So what's happened in Antarctica? I'm going to show a little animation from the GRACE gravity satellite that simply flies over Earth and observes changes in gravity. And changes in gravity includes changes in ice mass when ice melts. So it's a little animation that shows changes in the mass of the Antarctic ice sheet through time, starting in 2002, when these satellites were first launched. So let me see if I can start my figure. I have a little sliding bar here that tells you where we are. You can start to see some colors appearing where we are losing ice. And I'm just going to see if I can actually stop this animation a little bit. Yep. So here we've stopped in 2010. We can see mass loss from gravity measurements up along the Antarctic Peninsula. There's a big area of ice loss down in this part of the West Antarctic ice sheet, which is called the Amundsen Sea region, because we have the Amundsen Sea out here, the Amundsen Sea embayment, and this is a highly dynamic part of the West Antarctic ice sheet. We should also point out that there are some areas of ice loss in the Australian sector, and I'm going to come back to some of this later on in my talk. So there is some similarities between some of the dynamic changes we are observing in the West and what's appearing and starting to be observed in the East. Oops, started again. So here we have 2004. We've got a growing amount of mass lost in the Amundsen Sea embayment. The color scale here is meters equivalent of change relative to the starting point in 2002. So if we lose 1, 2, 3 meters of ice, that's actually quite a bit more when you start off with this ice loss being from snow, because snow is less dense than ice. You can see that the detection of gravity shows some change in the trend. Overall, we've seen this very steady decline in mass with a little sort of slight reversal in the trend in 2001, 2002, but it's not terribly different from what we observed in 2004, 2005, when there was also a slight sort of stabilizing influence. And that's tied to the fact that we also have some natural wind-driven, atmospherically driven changes taking place tied to El Nino. Is actually a natural climate phenomenon that not only influences Australian climate, but also influences Antarctic climate and Antarctic mass losses. The interesting thing is that if you start to look at these changes in terms of ice flow and mass loss, it's quite evident that those areas where we observe these changes is where the ocean is warm. So the left-hand side, the left-hand panel shows in the reddish color areas around Antarctica where the ocean is relatively warm. And when I say relatively warm, we're talking 0 to 1 degrees, and that is warm relative to the freezing point, which is minus 1.8 for seawater, for example. So there is certainly energy available in these water masses to melt a considerable amount of ice if that deeper water from the Southern Ocean flows across continental shelves and reach the ice sheet. There are regions that are much colder. The Filchner-Ronne area is an area that is currently quite cold. The side of the peninsula over here is also relatively cold and sheltered from these water masses. But around East Antarctica, we can see a combination of quite cold settings with some incursions of warm water in the areas where we are observing change near Thwaites Glacier, for example, and Cook Glacier down at the very bottom of the panel. So climate change and sea level, when it gets warmer, ice tends to melt, and in summer, certainly in Greenland and many parts of Antarctica as well, we get lakes forming at the surface of the coastal parts of the ice sheet. And in Greenland, this extends to several kilometers of elevation. In Antarctica, it's more on the ice shelves, but we do get the formation of these ponded water mass extending quite high up in certain parts of particularly the East Antarctic ice sheet, which has a somewhat lower latitudes than other parts of the Antarctic continent. So liquid water plays a role. As scientists, we are concerned that if we start to form more and more liquid water, this water could flow into fractures and crevasses and cause what we call hydrofracture. And hydrofracture is a process that is simply tied to the fact that water is more dense than ice. So if you fill up a fracture, with water, the density difference can exert enough pressure at the tip of this fracture to make it propagate. So we have watched and observed floating extensions of the ice sheets that have rapidly collapsed due to the formation of water and the storage of water in lakes and crevasse fields. And we are concerned about the fact that these floating extensions might be more prone to this type of catastrophic collapse, because when we do lose these floating extensions, the ice shelf part here, we can lose some buttressing effect from the grounded ice sheet, which has simply less mechanical resistance. That can cause the flow to speed up and for more of the grounded ice to flow into the ocean and cause sea level rise of a higher rate than we would have had without this type of event happening. So we're concerned about melt causing retreat, retreat causing acceleration and thinning, and for thinning and acceleration to become interactive in the sense that one exacerbates the other into sort of a positive feedback mechanism. Okay, so if we have a look at the latest report by the Intergovernmental Panel on Climate Change, this is a huge body of scientists that meets up every 6 to 7 years to draw up a consensus of where we are, what we know, what's the current level of knowledge, what can we conclude, how certain are we about specific aspects of climate change and its impact. And the Intergovernmental Panel on Climate Change operate with different types of scenarios, climate scenarios tied to how many greenhouse gases ultimately are emitted into the atmosphere. So we can have sort of rosy, positive scenarios where we stabilize anthropogenic emissions, or we can have business as usual scenarios where we are not really able to curtail our greenhouse gas emissions. So that's the scenario in the red social economic pathway in which the effect of greenhouse gas emissions just rises. So in the sort of fairly severe climate change scenario, we are seeing temperature changes relative to the pre-industrial era as reaching perhaps 2 degrees, 3 degrees by the end of the century. The Paris Agreement, of course, was an attempt to limit this temperature increase to 1.5 degrees or 2 degrees at the very, very worst. But that's not the pathway that we are currently on. In terms of sea level rise and these different climate scenarios, we are currently expecting sea level rise from projections of ice sheets and glaciers to be somewhere between perhaps 0.5 meter to 1 meter by the end of the century, according to computer models simulating ice sheets. But there is a tremendous amount of uncertainty associated with these calculations. We are much more uncertain about what sea level rise is going to be compared to what we think the global mean temperature change might be, because that's pinned to greenhouse gas emissions. So the dashed line from the IPCC report is an indication of what sea level rise could be if we start to run into tipping points associated with ice sheet instability. And that's simply what we are seeing on the right-hand diagram in a cartoon, this situation in which we start to see some of the world's larger ice shelves breaking apart due to the formation of meltwater on lakes and hydrofracturing of these ice shelves. And the sort of catastrophic scenarios in which a coherent ice mass becomes just a jumble up of ice blocks and icebergs. And we have seen that for some smaller ice shelves in many parts of Antarctica, but not the big ice shelves, of course, so far. So this is an indication. It's a dashed line in the IPCC report because it's extremely uncertain. It's not part of the agreed sort of likely scenario. It's something that at the moment is stated as being potential high-end scenario of sea level rise that we cannot rule out. And if we keep looking at this trend beyond 2100, we run into very high numbers of 5 meters by 2150 or 10 meters by 2300 or something to that effect. So for this reason, deep, potentially unstable drainage basins in Antarctica has received a fair amount of publicity in the news, often not good news, I'm afraid. Some of these can be somewhat alarming, and sometimes there are studies in science that show different things than others. I think it's true to say that we truly are losing pretty much ice in all areas of the cryosphere where we have ice. But the actual projection of how much that will equate to by the end of the century is something that we really don't have a very good handle on, apart from this sort of anticipation that it probably will grow more intense, but the rate at which this rate will change, the acceleration of the trend, so to speak, is really, really uncertain. Now, in the introduction, it was mentioned that I have been working on Thwaites Glacier, and that's true. There was a big American, British project set up about 6 years ago, and it's still ongoing today. In fact, we had our best field season just now to study Thwaites Glacier, and I think it was Rolling Stone magazine that sort of started calling it the Doomsday Glacier. It's not something we call it as scientists, but in the media, it's sort of got that nickname as being the Doomsday Glacier. It's simply a glacier that we're concerned about because everything points to this glacier being particularly sensitive to ocean heat and ice and this sort of loss of ice shelves and potential acceleration that could become this runaway effect, but we're not certain about it. So this Thwaites Glacier collaboration was set up in 2018 with support from the Natural Environment Research Council in the UK, the National Science Foundation in the US. And what was unique about it was the two national funding agencies got together and said, there are problems in Antarctica that we cannot resolve ourselves. We need to work together collaboratively in order to address these problems because they're in a part of Antarctica that is so remote that we simply cannot do the science unless we make it a team effort. So out of this international call came a quite unique program of 8 interconnected projects focusing on different parts of this particular glacier. And some of the projects would be completely ship-based and do oceanographic observations with mooring and ROVs, remotely operated vehicles sent under the ice shelf to look at how it's melting, how the warm ocean water from the Southern Ocean flows across the continental shelf. There was another project that is looking at the paleo record. How has this process panned out in the past? There's 2 projects on the ice shelf, people drilling through the ice shelf, putting instruments and moorings through the ice to observe the ocean underneath. There was a couple of projects, including the project that I was a lead scientist on before I moved down here. And that's is a project that's specifically looking at the boundaries of the drainage basin. And I'll get into that with a few more slides. Oh, I think I'm going over time here a little bit, sorry. Just a few field slides and field notes from the Thwaites program, tractor traverses in the GHOST project, did VibroSeis with these big tractors that did seismic investigations. The twin otter that you can see here, pulled out of instruments, is our project called TIME. And one of the rather amazing achievements that this project has allowed us to is to do the first fully 3D seismic experiment in Antarctica on the ice sheet, with 1,000 instruments put out on the ice to look at ice deformation and ice properties and the flow of ice in 3D and the interaction that fast-moving ice have with slow-moving ice, and the role of the bedrock beneath in controlling that. So I am going to wrap up now. It's going over time a little bit, but why are we scientists concerned about Thwaites Glacier? This is just a cartoon diagram to just illustrate that what makes Thwaites potentially unstable is this inland dipping slope. The grounding line, which is the line where the grounded ice comes afloat and is a pinning point. And right at that sensitive pinning point, it's important to be aware of we can start to have an imbalance in terms of the flux of ice that leaves the system and the flux of ice that forms in the drainage basins from snow accumulation. So when we get a retreat of the grounding line, it goes deeper. The amount of ice that fluxes out of the grounded ice and into the ice sheet goes up. That causes an imbalance in mass, and that causes thinning. That causes yet more grounding line retreat, more flux of ice out of the grounded ice shelf into the ice shelf, which is melting because there is these intrusions of the warm water from the Southern Ocean that is flowing across the continental shelf. And that's the mechanisms that we are very concerned could become a positive feedback loop or tipping point, so to speak. And that's why glaciers like Thwaites Glacier can undergo continued retreat that could end up potentially to be the loss of the entire western part of the ice sheet. So we're not certain that that's taking place in the West Antarctica. There's some concerning observations made to that effect. We know from models that this can happen if we force the models with a sufficiently high melt rate, but we really are in an area where we don't know whether this could be triggered by the end of the century or in 200 years or 300 years. The extent to which this is reversible, in the sense that if we manage to curtail greenhouse gas emissions, whether the ice will be able to recover. Now, finally, just to reiterate that the Australian parts of the Antarctic continent also have deep marine-based settings, and we really know very little about that. So it is just a cartoon diagram of Denman Glacier, which was the target of a lot of work in the Australian Antarctic Division and two big programs, the Australian Centre of Excellence in Antarctic Science, which I'm part of, and also another large program called SAFE. But Denman Glacier, where we just had a big field campaign, is a very interesting part. It's the deepest part of any place on any continent on Earth. So it's basically the deepest basin on Earth is Denman Glacier. So there is obviously a significant potential for this glacier to also undergo a rather major alteration in its configuration and flow. But fortunately, at this point in time, we are not seeing that as being in place, although its grounding line has moved quite a bit from 1996 to 2018. So we are somewhat concerned and keeping an eye out for this massive glacier. I think I'm going to leave it at that and say thank you.
Thank you, Paul. Look, every time I meet with you, whether it's online with a group of people or individually, I learn something new, and I've certainly been jotting down notes as we go this evening, Paul. So very fascinating insight. For those in the audience, I'm
You're breaking up a bit, Adrian.
have known Paul for some time now, going on 20. My connection is unstable. Can you hear me now?
Yep.
Right. So look, I'll leave my my video off, ladies and gentlemen. Are there any questions in the chat? Because as I mentioned, I've certainly got a few of my own that I might bounce off you, Paul, if that's okay. So look, while I have the floor, Paul, you touched on global sea level rise and changes that may evolve under different emission scenarios, etc. Do we have sufficient knowledge to know how those changes may or may not be greater or lesser around the Australian continent? If I see an average sea level rise, will that be more or less in Sydney or Darwin or whatever it is? Do we have understanding of pluses or minuses there or not?
Yeah, this is an area that I'm really interested in, but and you're really interested in, and many of us, Patrick in the audience, is very interested in. It's not something that we have a very good grasp of, and I think there is a bit of an awakening going on in the sense that we've been focusing a lot on this sort of global number. What's the global number? Sort of realizing that there, of course, are local effects like land motion going up and down. There's groundwater depletion rates from water use in certain areas that can cause subsidence as well. There's gravitational effects associated with groundwater storage that can attract, from gravity perspective, can attract more water towards the coast. There's a multitude of processes, including circulation around. Australia will also have quite a big role to say, and the difference between Sydney, Brisbane, Perth is actually quite surprising. Has been surprising to me. So we sort of know what many of these factors are, but putting them together and understanding how they will change when we change ice mass to a significant extent, even though it seems like far away, Antarctica is actually considered sort of near field in terms of sea level rise, and Greenland is something we should also concern ourselves about, even though it feels very far away. But that's a far field effect that has a really direct influence on Australia. So I think that whether we are worse off than the average, I think some people would say Australia is sort of close to the global average. But if you look at the figure that I showed, there's clearly are also some areas around the Australian coast that has observed rate of sea level rise that's quite a bit higher than the observed, which is sort of 3 to 4 millimeters per year in the last 20 years on average.
Thank you, Paul. Very much appreciate that. Look, we have got some questions flowing into the chat. I'm not sure if you can see those. Dave Guide has got the first one there. Can you see that, Paul?
A couple of questions.
Yeah.
David. Oh, hello, David. Nice to see you in the audience. That's great. David asked, can you speculate on what the unknown unknowns are with respect to ice mass loss? Ooh, the unknown unknowns. Well, those are pretty tricky ones, right? I think it's bad enough that we have a lot of known unknowns, which is for many years I have been fortunate to do a lot of field work over the last 20 years in Antarctica and Greenland and Canada, Svalbard, and for many years when I've given lectures about things like hydrology of glaciers, some of the observations that we've made, I'm basically telling students, like none of the things that I've told you about in this lecture that I observed directly in the field is really incorporated into the models that we predict sea level rise with. Things like what happens on the underside of the ice sheet. We sort of know that if things start to flow faster, we should have more friction. More friction means more frictional heat. More frictional heat means more meltwater at the base, which means perhaps lubrication or flow of water in some sort of subglacial plumbing system. None of that's included into the models. There's really complicated structural deformation processes taking place in the ice itself, similar to geology, where we know from escarpments like falls of geology creates a stunning display of a geological record. But for ice, it's the same. There's stunning display of deformation taking place. We just don't know it. And the challenge with glaciology, I think, in compared to, for instance, oceanography and climate science, is we can't observe the basal part of the ice sheet, and that's really where the action is, as opposed to we can observe the surface of the ocean where the wind's forcing is applied, or we can observe the atmosphere through satellites. We can't actually observe the bottom of the ice sheet. And it's the bottom of the ice sheet that dictates how the grounded part of the ice that stores the water that we're concerned about, that dictates the rate at which that's going to flow into the ocean when we start to tinker and warm the ocean interface. So that was a bit of a long-winded answer to that, but thank you, David, for posing the question. Should I just go to Freya's question?
I think so, Paul. Yeah, Freya's talking about infrastructure. Can you shed any light on that one?
Yeah, for sure. No, I'm aware of that. No specialist. I have only lived in Australia for a year now, but I've already know that we have Sydney Airport very close to sea level, RAF Townsville very close to sea level. Sea level is often very, great places to live. Here in Hobart, I live close to sea level as well. It's a very inviting environment to be in, and that also means that today we have significant infrastructure, and I can't actually remember what that number is, but I know that there is a number, and I think it's in the hundreds of billions that that are infrastructure values in low-lying coasts that are beneath the IPCC projected area of sea level rise. So, and globally, it's something on the order of 200. I mean, the low that lies below the sort of what we anticipate to be the direct inundation level from sea level rise, not even including storm surges and so forth, and this hundreds of millions of people. Like large cities in Shanghai is basically sea level. Ho Chi Minh City in Vietnam is at sea level. So there's no shortage of potential impact to be influenced and to require adaptation over the coming decades. Yeah. So yeah, that's true. Patrick writes, if one of the below sea-grounded glaciers facing Australia did retreat rapidly, what might the effect on Australia be? That's a really interesting question because, and it's not completely straightforward to answer, because when we start to lose ice in certain parts of Antarctica, there's a contribution to that goes into the global ocean, and it's a global sea level that I've talked about in this talk today. But we get rebound effects when we lose ice. The Antarctic continent is going up. There's an elastic rebound and there's a slower viscous rebound. So the whole Earth deforms differently, responds to that unloading. So the closer you are to where this action lies, you can sort of be influenced by that. You can go up, like as part of there's Greenland communities that I'm aware of that has risen over a meter simply because they live so close to where the ice is being lost. But this can also pivot the other way. You can get sort of land going up in one area and then pulling the ground down elsewhere. And the far field effect is, of course, that if we get uplift in Greenland, for instance, which is far from us, well, we should be adversely affected by that here in Australia. And this is this fingerprinting concept that we're hoping to explore more in future research projects. And it's really an intricate pattern that differs from drainage basin to drainage basins, both around Greenland and in Antarctica. So it's not going to be the same if it's one side of the continent that loses ice or the other. There's going to be a different imprint of that in terms of sea level at any given location around Australia. But we are really not very clear on that. But we are hoping to produce scientific research that will help us develop spatially distributed projections of sea level rise. Adrian asked, you've drilled to the base of the Greenland Ice Sheet. Can you do that in Antarctica? I would love to do that in Antarctica. I am hoping that we can do that. Drilling boreholes is challenging. It requires patience and but it's, in my opinion, not a very logistically risky endeavor. It's a well-known technology. You simply melt a lot of snow, you form a lot of water, you heat that water up to boiling temperatures and put it under pressure, and then you melt an access hole. And we've drilled about just over 1 kilometer in Greenland in about a day. Depending on how big you need that hole to be. And that's been quite important in understanding some of these complexities that we don't have in numerical models. Like how much deformation is there in the ice? What's the composition of the ice, the structural traits, and how fast does ice slide? And what's the role of water in lubricating the flow of the ice? So yeah, I hope we can do that in Antarctica. Now, Australia has the additional challenge of not only having an extremely large territorial parts to its claim, it's also some of the biggest drainage basins. It's some of the thickest ice. So it's no straightforward task to do that. But there are some places, and including some of these sensitive locations in the east, that are undergoing change, where I think we can nevertheless still use this technology to drill down and get some of this vital information that we need to constrain the models. Helen asked, have you seen the climate risk assessment the Australian government just released today? How would you advise that we plan for sea level rise along Australian coastlines? Ooh, that's a big question, Helen. Thank you for posing it. I am aware of the climate risk assessment. I'm not aware of the details and the report that came out today, but I will definitely go and have a peek on that tomorrow. It's an area that I shouldn't actually claim too much expertise. I've moved to Australia just a year ago. I'm making this, hopefully, my research. I'd love to do and be part of this type of work. I feel quite passionately about science and glaciology, providing more of an impact-based research output. So one of the things we're working towards is to come up with some actual projections for Australian coastlines that are different to these IPCC numbers, the Intergovernmental Panel on Climate Change, these global averages, which is what coastal planners and coastal adaptations are using to prepare Australia for sea level rise. And it's my opinion that we need to have better numbers to work with than a global average. We need to have something that is at the very least regional. But that requires a lot of work. There's the vertical land motion part that Geoscience Australia is working on. This ice sheet component and the glacier component that people like myself and Adrian and the history that Patrick's is working passionate about. How can we use the past as a key to understand the future? How can we deal with uncertainties in the past and relate that to uncertainties in the future? So I'm hopeful that in, say, maybe some years, it's not in science, things go slowly. We need to do new models and do things differently. But I think that we are at the cusp where sea level projections for adaptation planning will become quite a lot more detailed. But we're probably talking some 4 or 5 years into the future.
Thanks, Paul. Look, it's great to see the diverging questions here with perhaps some engineers and planners and the climate scientists. And I think the takeaway that I'm getting is that, as you suggest, we need a bit more detail, frankly, about how global projected sea level rises may impact particular areas of Australia, so that we can plan for infrastructure and adaptation, etc. Ladies and gents, look, I'm just keeping an eye on the time, and I'll hand back to John, please, our host, who will thank Paul and wrap up the evening. Thank you.
No worries. Thank you so much, Adrian. Thank you, Paul. That has been a fascinating discussion. I've learned more about glaciers than I was expecting, and very much well worth it. So thank you again to Paul. Thank you again to Adrian. As I mentioned at the start, this session has been recorded. We will be releasing it on YouTube shortly. Likewise, RGSQ runs a broad program of events and activities. I've just popped it into the meeting chat, some of the highlights of some of our upcoming events, including looking at the problem of the housing crisis and potentially some climate impacts there, a panel discussion at the end of this month looking at climate resilience in communities, starting into our lecture next month looking at conserving and utilising the Australian flora for food and energy. At the moment, we have our writing competition ongoing. Entries are open until the end of April. And on a polar topic, coming up in early May, we have a presentation during the day about navigation at both poles now and then with our map group. So check out the RGSQ website for upcoming events, register, come along, be engaged, and we look forward to seeing everyone at an event very soon. Once again, thank you to Paul, thank you to Adrian, fascinating topic. And with that, good night, everyone.
Thank you, John. Thank you, everyone.
Thanks, John. Thanks, everyone.